I'd like to start by acknowledging that the work I'm talking about is the result of work by a team, and I'm very grateful to all my mentors, my colleagues and peers, and students and postdocs who mostly went on to become colleagues and peers. I'm going to talk to you about Antarctic processes in the climate system, and I'm going to talk mostly about this area around East Antarctica, south of Australia and the Indian Ocean, with a concentration a bit on an area known as the Lambert Glacier-Amur Ice Shelf System. And I'm going to be talking about three different forms of ice and how they interact with the climate system and how they interact with each other. Firstly, in the centre, the white, the giant ice sheet of Antarctica, huge volume of fresh water tied up in that, presently contributing to sea level rise and with the capability of contributing much more in the future. Around the edge of the Antarctic are the fringing ice shelves. More than 50% of the Antarctic coastline is fringed by ice that's pushed into the ocean off the internal ice sheet. It's freshwater ice, but it's floating on the ocean and interacts with the ocean. And then each season around the continent, up to nearly 20 million square kilometres of the ocean freezes in the sea ice zone. That's ephemeral and a thin veneer on the ocean. It affects the transfer of heat, water vapour, gases between the ocean and the atmosphere, and it also changes the structure of the ocean underlying it. The ice sheet and the ice shelf system, like any hydrological basin, Antarctica receives its mass as precipitation in the form of snow. That doesn't melt, of course, it gets buried, slowly moves downhill under gravity by ice deformation, and is discharged back into the ocean. That process can take several 100,000 years or more from the time it falls in the interior till it gets to the coast. And unlike Greenland, where a lot of the loss in the coast is by surface melt, in Antarctica there's very little melt, even at the coastline, and the ice gets pushed out into the ocean as a floating ice shelf. And the eventual loss is either by iceberg carving off the front of those ice shelves or by melt underneath where the ice shelf interacts with the ocean. Now, any imbalance between the snow falling in and the discharge will contribute to sea level change. And it's been one of the big questions we've been trying to ask for a long time. The classical way of doing that was to look at the difference between the accumulation in the interior of Antarctica, the snowfall integrated over time and over the whole area, and compare that with the discharge near the coastline. And for a period of about 20 years, the Australian Antarctic Program concentrated on making measurements to determine that by doing large over snow traverses, very hard conditions, around about 4,500 kilometres of near coastline. That gave us a lot of information about ice dynamic processes, about the characteristics of the ice sheet, but inevitably it couldn't really answer the difference between this small difference between this large input and the large output. We got a hint of what was going on, but the errors were always too large to get a definitive answer. These techniques did, however, give us information to help us validate and calibrate the satellite systems that now enable us to estimate the ice sheet mass balance with some certainty. There are three different ways of estimating the ice sheet mass balance from space. There's, again, the input-output method. Only now we can measure the discharge velocity around the coast of Antarctica every kilometre or less using synthetic aperture radar interferometry, satellite-based techniques. And we can compare that discharge with the input estimated from mesoscale meteorological models validated against various data sources. We can directly measure the changes in elevation of the ice sheet by radar and laser altimeters, or else we can measure the changes in the gravitational field by satellite systems. And the gravitational field changes are related to mass changes. All these require some corrections. These are examples of some of those techniques. The top three presentations show the measurements from gravity satellites of the mass change. The red areas where Antarctica is losing mass, and quite extensive amounts of mass. It's concentrated in an area around West Antarctica where there's interaction between the ocean and floating ice at the edge, and I'll come back to that. The one down here in the bottom is direct laser altimeter measurements of ice sheet elevation changes, and again you can see the losses of ice in the red areas. These two, this one's the velocity field over the whole of Antarctica, the mass balance field, the accumulation field over the whole of Antarctica, and these give rise to the third method. Now, these three techniques give similar results. There's some spread in results. You can see this in this bottom left plot, which shows the cumulative contribution of the Antarctic ice to sea level rise over the last 20 years, or not last 20, but from about 1992 to 2012. It's contributed something like 4 to 5 millimetres. There are two different estimates there. They're based effectively on the same satellite sources, so using those three different techniques, but somewhat different analyses. Greenland is also contributing extensively to sea level rise, slightly more, and there's an indication that the rate of loss of ice on Greenland has increased. So together, the two great ice sheets have been contributing over that period about 14, 15 millimetres. So moving now on to what's happening when this ice gets to the edge and forms an ice shelf. The ice effectively enters the ocean system as soon as it pushes into the ocean and starts floating. So if an ice shelf disappears, it doesn't change the sea level, but it can change the drainage of ice from the interior because it does provide some buttressing on the ice that's flowing. So if this ice shelf thins or disappears, we'll get a greater discharge. And there's complex patterns of flow, melting and freezing that occur under ice shelves. And a lot of that is related to sea ice production. The sea ice forming in winter ejects salt in the underlying ocean, increases the density, get a plume of water that rolls back down underneath the shelf and can cause extensive melt at the base, some areas of refreezing, and there's also flow of other ocean warmer waters underneath the shelf. These are some examples of what's happening underneath the Amery ice shelf. This one shows areas, the one on the left shows areas of accreted ice, marine ice that's formed from ice crystals forming in the underlying ocean sticking onto the bottom of the shelf. Up to 200 metre thick layers underneath that shelf. That's derived from satellite techniques. I won't go into the details here. Again, from satellite techniques and combination of other measurements, we can estimate the rates of melt underneath the ice shelf and refreezing. This is back very deep underneath the Amery ice shelf, about 2.5 kilometres deep, and rates of melt there are of the order of 25 metres a year. The red areas, which coincide with the pattern over here, are the rates of refreezing near the northwestern front. Overall, there's a net loss of about 1 metre per year on average underneath that ice shelf. So the next thing we needed to do was look at what was actually happening in that ocean cavity. And we did that with a program over about a decade or so, sinking 6 deep holes through the ice shelf with a hot water drill up to about 700 metres of ice, and deploying instruments, oceanographic instruments and other instruments in the cavity underneath. And we saw what we were seeing also in the satellite stuff. There was this marine ice on the bottom, about 200 metres, but the bottom 50% or so of that was not consolidated, it was permeable. When the drill went through a point here, it made hydraulic connection with the ocean. This bottom 100 metres or so of marine ice was permeable and isothermal and much more susceptible to basically disappear if there's any change in the ocean temperature or circulation. And also these measurements within the ice shelf cavity and across the front of the ice shelf allow us to estimate how the ocean's interacting. We're getting a flow inland on the eastern side of what's called circumpolar deep water, modified circumpolar deep water. That causes melting basically under the front part of the shelf in this northeastern corner. Sea ice forming around here in an area called Polinia increases the density of the water, and that gives that salty water that rolls right back underneath the shelf and causes massive melt at the bottom. And from the measurements of temperature and salinity in the water and their change, you can estimate the melt rate underneath the ice shelf. And that gives us a similar estimate as we got from some of those remote sensing techniques of about an average of 1 metre a year. So move now on to the role of sea ice in affecting some of this ocean circulation. When we first started working in the sea ice zone, we were really limited to working on what was called the land fast ice. That's that area only 20 to 50 kilometres from the coast where the ice freezes in the autumn and it grows slowly as uniform slab, continuous slab over the year by freezing on the bottom. And we were looking at how that ice, the thickness of the ice and the change from open water to ice affected the exchange of heat between the ocean and the atmosphere, and also how it changed as the ice grew and ejected salt, how it changed the salinity profiles in the underlying water. When we were able to make measurements in the much greater area of sea ice down that surrounds the continent, we saw just how truly dynamic it is. Most of the sea ice is what's called pack ice, pieces of ice that are driven mostly by the wind but also by ocean currents, and it moves at speeds of almost 20 kilometres a day. It can reach speeds of up to 60 kilometres a day in strong wind events. The circulation to the west in the east wind drift close to the coast, with some areas of divergence, and then moving back in the Antarctic circumpolar current and the westerly winds. And with that movement in that direction, you get divergence to the north, so the pack ice is always opening up, forming new water. Going into the pack ice, when we first got ships that were capable of doing that, we saw just how truly heterogeneous, how different it was in different areas, different patterns of ice forming according to the wind conditions. And snow on it was really quite limited because the ice is fairly thin. Once you put a fair load of snow on it, it depresses and floods, and you can form new ice from that flooding. This is an ice core taken. You can see different crystal structures, but when you take a deep core through thicker ice, you can see this repeated cycle of stacked flows. And it's the dynamics that really determines the nature of the pack. When the ice field is divergent, you open up new areas of open water, you very quickly form new ice. When it compresses, you start stacking it up, so the thickening to make ice over about 40 centimetres occurs by this convergence and ridge building and rafting. And I was going to talk about that, but I think I'm up to 10 seconds, so I'll leave it and talk to you later about polynyas and large-scale ocean circulation.
Thank you, Ian, for sticking to the time. Are there any questions? Maybe let me start off with one. And in the early stages, when you were showing the sea level rises, in 90s there's a negative values. Means, if you look at the plot, and do you know what do you mean by the negative values? Is it because of
that means for that particular period? It was only a period of 1 year, and it's probably outside the error bounds anyway. But okay. There was a greater snowfall than there was discharge, and the snowfall is variable on timescales from year to year, where the discharge tends to be integrated over much longer periods.
Are there any further questions? Matthew?
Ian, one of your very early slides had 58 metres of global sea level locked up in the Antarctic ice sheet, which is an amazing number, and you can go back into Earth's history many millions of years ago and find a time when a lot of that was melted. Is there any chance that rather than say metres of sea level rise for Antarctica, in the future, hundreds of years from now, we might get tens of metres of this slab of ice melting?
Yeah, there is. It's a thing called the marine ice sheet instability, that when the bedrock slopes down backwards, that you can reach an instability. Once it starts decaying, it can accelerate and you get more discharge. Most of the estimates, I think, the next century, I'd say we're not going to get more than about 40, 50 centimetres of sea level rise. But what's going to happen beyond that? Once these processes start, they're not going to stop at the end of 2100. They're going to continue and even accelerate. So there are indications we could have several metres of sea level rise within the next few hundred years.
Okay, if there are no further questions, could you please join me to thank Dr. Ian Allison?